Hi. So I will try to explain you some intuitions. Also, I will show you some questions, but I will try to give you more intuitions that you need to know when you're training neural network. Okay, so today actually we will talking about optimizations of neural network, and next week we will combine it with convolutional neural networks. But it's actually the basis of the all neural network that we have at all kinds, with a little bit corrections, but it works for all kinds of neural networks. So it's really basics that you should know. So we will talk about regularizations and optimization challenges and how we can actually to overcome on them. So let's start from object and loss function. So as you know, common objective and actually for classification correctly, for each input we have the output of neural network. So we have for our y its function of some fx. So it's indicates a probability measure over some set C, and our classification is taken as our maximum argument of yj. So j is all our classes. Okay, so in order to create this normalized measure that we need for this our classification, because we need a number between 1 and 0. Yeah, so we actually use some nonlinearity. It's softmax function. We have talked a little bit about it in the last lectures. So this is our softmax definition. So actually it takes over all samples and normalize it. It measures the probability of our sample to be one of the classes, okay, by normalize of all probabilities, and it's actually the common and standard way to do a multi-class cross entropy regression. Okay, so again. No, yi it's a prediction in the yi is a prediction in the specific place in some class. Okay.
Yes, xi it's not the sample.
Xi is the sample in this place. Okay. So you are taking taking your target prediction, and then you try to predict the probability of given sample to be one of the classes. Yeah. Okay. Yeah, and then we normalize it by other probabilities. Okay, so it's always function. It's the softmax output always between 1 and 0. Yeah, 0 and 1. Okay. Yeah, it's a little bit of another formulation.
It's not
it's not the sample itself. It's the output of the.
Yeah, the xi it's the output of it's output. Yeah. So okay, so a little bit. So it's a little bit other terminology, but xi it's the output of the previous layer. Okay, and then you are actually normalize it to your classes probability. Okay. Great. So the error function for cross entropy or of regression is actually minus sum of this log. Okay, so when we consider that t is our indicator where our ct is correct label. Okay, so if j is equal to ct, it's actually 1. Okay, so we have correct label. Otherwise, it's 0. Okay, so we want to minimize this cross entropy, this loss. Okay, so actually we get some terminology that calls negative log likelihood. Okay, so we want to minimize this function. Okay, so you seen it in the lecture. Let's talk about real intuitions, how you know if it's good or not good, or how we can generalize our or getting better performance. Okay, so neural network usually specifies it's actually designed to have more parameters than the number of training samples. Okay, it's actually not rule, but it's a common practice. Okay, so common practice that we should be aware of. It's that the number of our parameters should be greater than the number of our samples. Okay.
The number of parameters is given by the problem.
When I'm talking about number of parameters, I'm talking about my model size. Okay. So if each you are actually you can decide how many parameters you have in your neural network. Okay, by increasing or decreasing the number of hidden layers, the filter size, the layer size. Okay, we will talk about it later. But you can decide to use more or less parameters. Parameters is actually our weights. Okay, and the common rule is that the number of parameters should be greater than the number of our samples. Okay, so actually we are talking about that if you can, for each sample we have one parameter that can specify it. Okay, it's not actually it's not what actually happened there, but it's a common practice that you should be aware of, and it's actually most of the common neural networks are have actually just this rule. Okay, questions, guys? Okay, great. So this is usually a bad idea when considering a model in classical learning theory. Okay, in classical learning theory, it's actually a bad idea to do it because why do you think it's a bad idea in classical machine learning methods? Overfit. Yes, very good answer, because actually from now we will fighting against overfitting. Okay, it's one of the common problems that you have in deep neural networks. You have overfitting, and who ask what is overfitting, we will talk about it in a few slides. Okay, so turns out this crucial for training, where the networks with large number of weights are easier to train. Okay, so we will use some regularization to fight against overfit. Okay, in some respects we will use okay, it's like blessing of dimensionality. Okay, so high dimensional weight space combat, it's actually a curse of the dimensionality. Okay, so what is overfitting? Overfitting is when we train it's when we training. So on our training sample we gave better accuracy rather on the validational set. Okay, so we in training you have two sets. One is for training and the other for validation, when your parameters are fixed and you also are deploying your neural network and measuring your accuracy. Okay, so when actually you can okay, so overfitting is actually here. Okay, so this is the overfitting. We have very good classification on our regression problem on our training set, but we have the gap between this and this is very high. Okay, so this is actually our training set, and the validation set is going to converge, and then it's actually not converge here. Okay, So this is the overfitting. So regularize. It will not overfit on validation data. So so overfitting it's when it happens, and underfitting. What do you think? What is underfitting? Hmm? Yes, underfitting is when you have not enough. Hmm? Yeah, it's not too simple. You can actually you can see it like you have no enough parameters to define your task. Okay, so if your task is not your number of parameters of your model is not enough to define your function, your function, you have no. It's actually underfitting because you can learn. With when you have underfitting, you can actually get results at all because you can non-train your neural network. It will achieve. It will not converge. Okay. Great. Overfitting, it's the samples that you are using. Okay, so a few words about the training process. In standard training neural network problems, you have around 16% of the data for training process, 20% to validation set, and 20% for test. We are not. Will talk. I will talk about you later or why you need your test set. Okay. In the most cases, we are using only with validation and training set. So the number of samples for training is much more for the number of the parameters of the samples that you have for validation. So overfitting is when you trained very good for this 16% of your samples, okay? But it was too good. You too good now to classify your 60% of data, okay? Sure, overfitting is a problem, but you have when you can declare very good, okay, define very good your function, okay, your function your f function, okay, of your model. Yeah, and then for the 20 for the another 20% that are used to validation stage, you actually achieve less accuracy, much less, because you trained very good for the validation set, okay, for the training set, sorry. And then we will have some techniques how we can make the model more generalized, and that we will achieve the same accuracy or very close accuracy for validation and training that set. Questions until now? Great. So we will start to talk about how we actually can fight overfitting and how we can stop it. So the simple and the most basic way to stop to make your model regularization is to use early stopping. Okay, so using early stopping is actually to train until you have your validation loss is getting the minimal. Okay, until your validation accuracy is decrease. When it starts to increase, and it could happen in the overfitting, as I saw you here. Okay, so actually we will train until which point? Till this point. Okay, because here, guys, take a look. Here, the validation loss is the minimum. Okay. When you train more, your accuracy is getting your loss is getting higher, and your accuracy is getting better. It's getting decrease. Okay. This is the basic and simple way to actually to learn. To train your model and to fight against overfitting. Okay. What you thought about what will be your role to stop your stop your model training? Yeah, no, validation. But why? What the other way to do it, or more intuitive way to stop the training? Yes, yes, yes. The actually the naive way or intuitive way, it's training until your training it's get converge. Okay, but this is actually not true. And when you want to fight against overfitting, you are use early stop. Okay, it's early stop. It's not a real stop because your training loss continues to decrease, but you are stopping anyway for getting better results on validation set, of course, because it's actually your result of your model. Okay, it's what you care about. Yeah, you're talking about that in this term you are not getting the local minima of. Yeah, yes, I agree with you. Overfit, I agree with you. It's actually okay. You can. It's one of the dangers of early stop is not getting the local minima, but it's actually your okay. It's your pitfalls. Okay, it's your it's some problem, and you need not all. Yeah.
Also, not something that you really should worry about because you can't assume that the data that you have really is a good estimation of the entire data in the world. So you don't know if you have pre-existing biases in your training data, and saying that okay, I just trained a single batch is like, in effect, the entire training data is a single batch of the entire world. So it doesn't really matter if you train on your entire training data or the single batch. So I think it's per epoch. So you take. No, what he said is that when you stop doing, you see it increasing. What I'm saying. But this figure is per epoch. No, I didn't.
This figure is per epoch. Okay, and you talked about batch. But yeah, actually, your question is very good. Using log.
It can also happen in an epoch, no?
Yeah. Again.
It cannot happen in a.
No. This is epoch.
Yes, but we have a local interest in an epoch that doesn't really affect the.
In essence, your entire training data is like a batch on its own because you don't have samples from the real distribution function. It's not really.
Again, you're right. Early stopping can avoid you to get local minima, but you must when in some cases you prefer to do it. Okay, because you prefer to get best accuracy on validation set. Yeah, but you're right. Okay, so this was the early stopping. Okay, so the second technique, the common technique for regularization is actually a data augmentation. Okay, so each data for each task you can use for data augmentation, and we do it every sample by shuffling the data. It depends on your data and the data augmentation that you can use. Okay, so if our data is images and we are talking about classification on detection problems, so the common data augmentation is adding white noise, or making flip or rotate your picture, okay, to make it more to generalize your network to adjust adjust weights to some changes in your samples, okay. If we are talking about NLP language data. So we are talking about use some change words or change sentence, okay, or adding some keywords that it also can reduce the overfitting and help to regularize your data. Okay, so weight decay. So now we will talk about some penalties that you can use, you can add to your loss function, okay, to obey your model, get some behavior, okay. So the first one is L2 regularization. Is actually we add a term of L2 on our weights here, okay. So we add some L2 norm or our weights. Actually, it's equivalent of decaying the weights in each gradient descent step. Okay, so it's actually will help us to minimize our weights. Okay, minimize our weights and actually get our SDG problem more smoothness. Okay, so your parameters will be minimized and normalized, okay, and then you will help your gradient descent to find a better way to your optimization problem to optimize your function. Okay, so here you have some parameter, and we will talk about him later. Why we use it's hyperparameter. Okay, what I mean by hyperparameter?
Just by some restricted thing.
Yeah, hyperparameters that you can play with him. Okay, you can change him, and it's external parameter. Okay, it's actually you as a developer can change it for each execution of your neural network of your training. Great. So there are a lot of terms that people actually investigated, and a lot of papers are talking about some very sophisticated methods to add some terms. So it was L2 norm. Here someone present L1 norm. Okay, it's penalized like L2 by only you're taking the actually L1 is it's without the root square. Okay, so and other function like hidden using hidden activations H within network H. Okay, so here we use some L term L1 loss on hidden activations. Okay, there are a lot of other ways. So this two is working on parameter normalization, and this one is using on activation normalization. And I will present you in the next slide, I think, some most common way to normalize activations. What will be the name of the method? Normalizing the activations. Normalizing the activations, not dropout. Normalization. The activations is, yeah, but you're biased. Okay, so we have some, yeah, he taking course third time. No, just kidding. Okay, great. Okay, dropout. You talked about dropout. So dropout is very common technique. Most of convolutional neural architectures use dropout for as regularization technique. Okay, so how is actually dropout works? Dropout works, but in training we actually turn off some of our connections. Okay, actually we have a neural network. We turn off some of connections. So you can see it's our standard neural network. We have it's actually two we have here two hidden layers. Okay, so it's fully connected layers. Each layer is connected. It's connected to all his previous layers. Okay, so what we do in Dropout, we are actually turn off some of the connections. So we have less connections between the next neurons, and actually we turn off the dependencies of the next neurons to his previous layers, previous neurons. Okay, so this is actually also work as regularization, because why? Why do you think the dropout is actually help us to avoid overfitting?
Less parameters.
Because the next parameters are less dependent on their anchor cells. Okay, so you're actually taking less parameters into account to some classification, to prediction of some sample. Okay.
You are doing this dropout for each sample.
You are doing this dropout for each epoch on
The same dropout.
this, for the each epoch the same distribution. Yeah, you are actually how we do it. You are distribute your actually you take, if commonly we are taking from 0 to 0.5. It's actually the number of connections that you remove. Okay, and the distribution of how you sample your connections is by normally we are taking or Gaussian or Bernoulli distribution to find to decide which of connections to remove. Okay, you are doing it only on training. Okay, you are doing it only on training stage. When you are doing your validation, you have no use on dropout. You're taking your all weights and all activations. Okay, you are taking actually this neural network. Okay, you are propagate on validation. You propagate all samples through all parameters. Okay. Yeah.
When we don't propagate here, we don't take the weights out.
Yes, you're taking all weights, because all weights in the all training process you use all weights. Yes, in the training process you use all your weights, but you are each epoch you use another weights. Okay, from your sample from your distribution. So you are taking for each sample you are taking 40% of weights, but this 40% are changed. So in the final you are taking all your weights, okay? But some of the weights are not contribute to your accuracy in specific in specific epoch, okay? Yeah.
Contributing means zeros.
Not contributing, yes. Not contributing is putting zeros there, okay?
All the biases.
What? Yes, all the biases, yes. All the biases. When I'm talking about weights, I'm talking about biases, because there are some version of unbiased neural network, but yes, if you're talking about, if we have biased version, so we use it. We apply our dropout also on devices.
The bias on the same neuron?
On the same neuron. On the same neuron. The biases that actually, we actually have the number of biases as number of the output neurons. Yes? Yeah. Yeah. Some questions until here. Or not some, all questions until here.
PyTorch it's implemented.
Dropout. Of course. Yes. Next tutorial you will see in all these actually examples of neural networks with dropout and other things, okay, and other regularization techniques. Some of them you will implement by yourself at home for your joy. It's very interesting. Yeah. So yeah. Other questions, or we continue? Great. So this is dropout. So actually we talked about it, but there are multiple explanations of success of dropout. Okay, it's actually about encourage redundancy with a neural network and our dependencies of specific unit to previous units. Okay, it's actually can be seen as model averaging techniques on our as 2 power n different model are used under expectation with when we are evaluating our neural network, and it's actually the multiplicative noise, or actually we use you can see as dropout as adding noise to your model. Okay, so it's like using noise, and believe me, you will love noise. Okay, noise help you. Okay, because noise actually do a few things. First, it's actually help your gradients to be less amenable to some change. Okay. The second one is it's help to regularize the neural network to make it more adjustable to not to be specific to some sample, okay, or actually to generalize better for all samples and not to specific one. And so it's actually you can see as dropout as adding noise, because we are taking and some adding noise for getting zero in the place where we are want to turn off our weights, okay, our connections. Great. So, is it clear? Some questions about dropout noise? What we are doing here? No? Okay, great. So, this is actually this is the surface of our optimization of our non-convex problem. Okay, so this is actually we actually are flowing in this surface during our training, trying to get to some global local minima, but in both cases we are actually getting some good local minima, okay, but not actually the best local minima that you have. It's very challenging to dealing with non-convex problem, and you have no some proof. You have no some proof that you will get your global optimization, okay? But we can try to find them. We can try to reach this global optimization, okay? So, efficient optimization of neural networks. Okay, so some of the obvious difficulties is actually we have strong dependence on initial weights. So first, when we are starting, we initialize our weights, okay, and in some cases, it's actually our first stage. Actually, our first we are landing on some surface, okay, and if we are landing not in good place, it will be very hard for us to get into this. To try to reach to our global minimas, okay? So possibly poor estimation leading to noisy gradients, okay? And noisy gradients is the gradients that actually not help us to optimize our model, okay? To getting our desirable changes on our parameters. Exploring high dimensional space using only local information, okay? So if we have some high dimensional space of our data, but we are use only some local information that not actually define all our space, it can give to difficulties to reach good optimizations. Great. So let's start from naive SGD. So we actually talked about it before on the lectures and on the tutorials. So it's actually our update rule. Next parameter, it's the next parameter value it's the previous one minus our step epsilon multiplied by our derivation of the loss. Okay. So this is actually using this as it's called vanilla SGD. Okay, it's it's only stochastic gradient in one direction. Okay, because you are only going in direction of the best, actually your derivation. Yes, but it's only one your optimization on one axis. Okay, so we will explain what. One of the dimensions of yes, it's one of the dimensions of our optimizations. Okay, so the later we will present a more sophisticated way to do the optimizations by two directions. Okay, so it's usually helpful to anneal our learning rate over time. Okay, why we want, what is actually annealing learning rate? So annealing learning rate is actually change our learning rate over epochs. Why you think we want to change our learning rate during the epochs? What can happen? What is how your surfaces look like? So why you think that we need to reduce the learning rate or your step?
Getting close to the local.
Yes, great answer. You're getting close to your local minima, and if you actually if your steps is if your learning rate is too high near the local minima, you actually will not never get in the local minima. Yeah, like the ball. Yeah, so you need to change your step, to reduce your step for getting to these curves, small curves. Okay, so what we actually do, we are annealing or we are reducing. It's actually a few ways to our exponential decay or smooth decay. It's actually the ways to reduce our learning rate over the time. Okay. It actually works. Both of them works great. Okay, we over the time we reduce our learning rate over the epochs. I'm talking about every epoch, not every epoch, but you can actually start from, or you're doing is all epochs, or you can define some epochs when you can start your annealing. Okay, and then you get better optimization in this way. Okay, against I'm using only SGD now, only SGD and annealing by annealing this step. Okay, so this step. So here I presented step that is fixed step, and here it's we change our step. Okay.
You actually use only the iteration number.
Only iteration number of parameters. Yes.
Makes sense to use the difference or the magnitude of your loss function. The closer the loss is, the smaller you need your learning rate.
Again.
At the first iteration, the difference between your labels. And
Yes. You're okay. So you're talking about when our losses decrease, we should. Yeah, actually, it's what happened. Yes, it's actually it's why we decrease it over time. Yeah, so it's actually when we decrease our loss, when our loss is getting smaller, we're starting to we decrease more and more. Okay, it's one of the techniques. Okay, yeah, but again, all of these techniques work great. You can use some exponential or just multiplication. It's work very good. There are no real evidence that one of them work better than another. Okay, so let's take a look on our plot. So this is our epoch axis and loss axis. So the red curve is actually good learning rate, okay? Because we have some, we are converged to some good point, okay? Some near zero, and actually it's what we should to try. It's what we should to get in good training model, okay? Yeah, and take a look on the high learning rate. So if you take some high learning rate, you will start you will start to reduce your loss more dramatically, but you will not get your some local good local minima because of the problems that we talked before, because we are not we can't we will get off our curves. And low learning rate will get some behavior as presented in blue curve, okay, and very high learning rate will get you some out, okay, you will diverge very quick. Yeah.
You talk about getting a good local minimum.
Yeah.
Now, how do I know I can get a good one and not just some random one?
Look, in the well-declared problem, your training accuracy should be near zero. Okay. This is good. In most of the problems that you will deal with, your training accuracy should get very high results. Okay, and this is good. Okay, this is good one. Not good is actually that your training accuracy is very high. Your training loss is very high.
So we won't be dealing with surfaces like the one you showed?
Again?
Like the one you showed before, surface?
Yeah.
You could have started like at the end there where everything was very red.
Yeah.
And not even gotten to the blue area.
Yeah, so you asked me if we are going to deal with these surfaces. Yeah, we in advanced tutorials we will talk about some more sophisticated, some more complex problems and the way to solve it. Yeah. For now, no. Okay, so guys, I will. Okay, so AGD with momentum. So momentum is actually the second direction that I talked before. Yes, it's one of the. It's actually give us some intuition to where to the direction of your gradient of your optimization, your gradient. So actually we will use the momentum here, and we will update actually our weights depends on our WT and on our VT. So VT will be some extension. It's our momentum. Okay, so we will set momentum. It's a hyperparameters. Usually we use around 0.9. Okay, and it can help us to achieve better or to converge faster or to achieve better results. Okay, great. So take a look. All HGD and HGD with momentum, it's optimization techniques that there are no change in any adaptation to learning rate, to your results, okay? Because we actually fixed it, okay? So these methods actually we are taking in turn what happened to our gradients, okay? So actually it's where our model process. So the first of this is undergrad. It's adaptive learning rate that actually have conditioned each gradient element with actually its estimate of its variance, making it inversely proportional to high noise to the direction. Okay, so it's actually we will take we will eliminate our gradients that if we see that some of the gradients connect to some samples, okay, and actually change, okay, so we will try to reduce our learning rate step, okay, and where we will see that that our parameters are not aware, are not not aware. They are not they are not participated they are not participating in our classification problem. Okay, so in these parameters we will higher our learning rate. So if is it clear, or repeat again? I will repeat again. Look, we have weights. Some of the weights, okay, are very essential to prediction of our model. Okay, some of for some samples, some of them are efficient for other samples. So for these samples where these weights are efficient, we are reducing our learning rate, okay? And where this is sufficient, we will actually getting our learning rate higher, because it's not enough to it's not enough to getting to top for our optimization. Yes. Okay. So these methods, ADOGRAD, RMS prop, and Adam, each of them are aware of our gradients, okay, of the influence of gradients of the parameters to the to our final classification, or to our final output. Is it clear, guys? Yeah. Some questions. Actually, we are okay. So okay. No, I want actually to talk about batch. We have a few minutes. I will talk about batch normalization. So batch normalization. So why we need him, and what he is actually doing. So it's one of the popular generalization techniques that normalize our activations in each layer. Okay, it's by normalizing the activations of each layer with some statistics from the batch, and we have two parameters that we are learned. Okay, so we can learn parameters for normalize our statistics over the batches. Okay, there are a few evidence why it works. So one of the it's not actually evidence, it's one of the hypotheses. So it's possibly because normalization is simple differentiable. Okay, so because its operation is differentiable, it's another parameter for that we can actually use for our optimization, and it's help to our generalize your model. The other is it elevates a lot of headaches with properly initialization neural networks by explicitly forcing the activation by adding Gaussian unit behavior. Okay, great. So take a look on the So how it's actually when batch norm is help. So if we have in our training set a lot of samples of, do you see it's black cat, okay? These samples have cats, but it's actually orange cat and gray cat, but okay, but it's cats but with other colors. Okay, so think that we are in our training set, we have a lot of cats that have actually a black color. Okay, so this case, if we will not add batch norm, we will not classify good cats that have another colors. Okay, because your model will aware that he needs to find that it needs to find your cat, and actually he will add the neural network will add his color to one of characteristics. Okay, but you want to actually to remove its color from the characteristics by actually generalize. You actually want to classify cat, not the black cat. Okay, so you will use, we will add batch normalization. Okay, it will add covariance shift to our problem, and then actually we will remove the dependencies of the colors to our classification target. This is why batch normalization works. Guys, is it clear? Some questions? No questions. You can ask me privately.